All right, Alex, what's the topic on day 4? Can you read it right from the paper?
We are in instantaneous velocity versus average velocity.
Okay, very good. So we're gonna stay there for the rest of class, and it's the only way I can teach that is through a graph. Did I provide a graph for you on that? Okay.
Similar to the one on the
Does it
board.
look something like that? I was trying to catch the gist of it. It's hard to do. All right, let's define these two terms first. Instantaneous velocity and average velocity. Instantaneous velocity is velocity in an instant. You're not supposed to use a word to define a word, but everyone knows what the word instant means, so we are going to do it.
Everybody says you're not supposed to define a word with a word, but the dictionary always does that.
Does it? Oh, bummer.
So annoying. I'm like, still don't understand.
Really? Well,
Or
that's
just like-
the marks of a poor dictionary.
Oh yeah, it's like
I'm like, what's
instantaneous.
seeing? It says the act of seeing. I'm like,
In
that's
an
not
instant.
explaining
in
what
an
it
instant,
is.
and then in an instant says, see instantaneous.
All right, instantaneous velocity is velocity in an instant of time. That's an extremely short instant of time, measure of time. Average velocity is velocity average velocity is going to be the velocity over a period of time. So far, like in lab class, and you might mention this in some of your write-up somewhere, were we establishing average velocities or instantaneous velocities in lab class? Which one? Emily Martin, which one do you think we were doing? Were we doing velocities in an instant or velocities over a period of time? In lab. Which one?
Average.
It was. So, how would we, if I had changed the lab and I said, I don't want these silly average velocities, I want instantaneous velocities, how would you have conducted the lab a little differently? Any ideas there? Because you did the period of time here, the period of time here, and the period of time there on the board. So what could you have done differently to get an instantaneous velocity? Zach? Is that noise too much for you? It's just so stuffy in here. I hate to close the door. Zach,
Just
what can I?
take the first one.
The first one, which you mean when we measured the top of the board?
Yeah.
Actually, this is more instantaneous than this because this was a shorter time than this. Does that give you a clue what you could have done to get to an instant of time? So what he said was partially true. He's going in the right direction. Can you improve on it? Here, we measured this amount of time and did it. And then here, so this one was more instantaneous than the other. So what could I have done? I could. Brandon?
I mean, you could try to find the speed of it at a certain point.
Yeah, well, how could you do that at one point? Because speed is distance divided by time. So how are we going to get time, or distance even, at just say that one point? Well, what I'm aiming at is we could shorten this interval. Suppose instead of here, I'd asked you to time it from there to there. That would have been a shorter amount of time. Is it an instant? All right, what if I had you do this? Would it be closer to an instant? Is it an instant? All right. What if I keep cutting these in half, and everyone's had that kind of paradoxical thinking presented to them before? Will we ever get to an instant doing that? Not really. So it's kind of amazing, almost miraculous, that we can come up with an instantaneous velocity, and I'll get to teach that to you with this graph. So enter the mathematician. So the mathematician comes alongside us and does for us in math what we can't do in lab. So in part of your write-up, could I encourage you to use the words instantaneous and average velocity? Just mention that these are closer to instantaneous than this one is more of an average. So they're all averages, but where these, the top and the bottom, we're closer to an instantaneous velocity than the entire board. Incorporate what we're learning in your conclusions. All right, instantaneous velocity is in an instant, average is over a period of time. The mathematician is going to teach us what it is at a given instant. Looking at the graph, you have to recognize what kind of graph it is. I'm not sure if I cut this off on your graph or not. Does it say position versus time on your graph? All right, if not, write it in. Because every graph has to be, have its axes labeled. So position is what we were thinking of as displacement, same word. So displacement, we could have said displacement versus time. That would match better what we've been learning, but position means the same thing. So if you could take your pen and stick it in the air, give yourself a starting point in the air. Pens ready? Brian, put your pen in the air.
Yeah.
Dramatic pause while.
There.
All right, put your pen, pencil in the air, and I want you to hear this object starts at 0. So you're at 0 from your viewpoint. I'll go in the same direction. From your viewpoint. Now, in 1 second, this I don't have a good. You can look at your graph for these things. Maybe you can help me with it. Could you read it, Emily Davis, at 1 second? Read over here the position of 1. It went to 1. So move your remember we're studying motion and it's only going to go like this, back and forth. It's very exciting. So we're at 0 and we've moved to 1. All right, Emily, where is it at 2? Can you read?
2.
It moves to 2. What about 3?
4.
4. Move 2 more to the right. What about, where are we? 4.
6.
6. Move over. 5.
7.
All right, what amazing, and 6?
8.
What amazing thing happens now, Emily, at 7? And goes to what?
2, 7.
All right, so now when we go up here, it's coming back. And then 8
4, 5.
and 9
3.
and 10. All right, it doesn't come all the way back, does it? So the motion that this graph, a lot of students feel like the motion that's graphed is this. It is not. The motion is it went down and it came almost back. Are you able to read that position time graph and explain that to me in another scenario? I hope so. All right. So that's an explanation of what the thing is doing, but once again, I'm looking for instantaneous velocity. Let's pick a point. Let's say we are looking at time 1 and time 6. Time 1 and time 6. So put a dot on your graph at time 1 and time 6. Draw a line, draw a light line that connects time 1 to time 6. So draw a line between time 1 and 6, and now make a triangle out of it. Make a right triangle. I'll switch colors so you can see. The blue is what I want you to put on your graph. In mathematics, we have learned to come up with a calculation that represents the tilt of this line. We don't call it tilt, though. We call it slope. So slope from our math life is the change in y divided by the change in x. In this case, it's the change, the y-axis is not, that little triangle is changed, we've met that already. The y-axis is not y, we call it position, so I'll say change in x. And the x-axis is not x, it's time. So what does that look like to you? Change in x over change in time. What is that? An old friend already, an old friend. What is that we've studied? Emily Martin.
Displacement.
Displacement, that's right. So, I'm sorry, not displacement. This is displacement.
Velocity.
Velocity, that's it. So velocity has shown up on this graph as the slope. Big deal, like tremendous deal. Amazing deal. So write it and start and underline it. The slope of a position, or we call displacement if you want. The slope of a position versus time graph is velocity. So let's just find the slope of that particular blue line. I'll emphasize the one I'm looking for. The slope is right there. So change in y over change in x. So change in y is y2 minus y1. Change of x is x2 minus x1. These are old math friends. So on this one, the point was, Emily, I have to borrow from your chart again. It's 6 for the x-axis. Again, what is it about for the y? 8, 6, 8. And this one, was it at 1, 1?
Yes.
All right. Or was it?
Yeah.
Okay. So let's do the math. Change in y. This is the x, the y. So we have 8 minus 1 for the change in y. And I'll put it right under the formula here. So 8 minus 1. And the change in x is the two first coordinates, 6 minus 1. So we get a 7 over a 5. The slope of that line is 7 over 5. Is that an instantaneous velocity? It still isn't, because what we've done is we've gone from 1 to 6 seconds, and that's not very instantaneous at all. So what we can do with the graph, however, is shorten it until we actually have a true instantaneous velocity. Let's find a spot where it can be easily found. Let's look at the slope at what point is really sort of flat. I don't think I have one in front of me. Where's yours? Maybe right there. Let's do the instantaneous velocity at point right here. Let me see if it goes as far as 2. Where's your graph? Not quite. Let's do one right here where I was with, and I need another color. So we'll go to orange. Let's do the slope right here. I am going to miraculously figure out the instantaneous velocity right there at point x, where the time equals 1. So can you draw what is called a tangent line to the graph? A tangent line is a straight line, and it only touches the graph in one point. So right there is a tangent line. What is the slope of that tangent line? Well, I'm going to make a triangle out of it. And did you stop the video?
No.
Okay, stop it one more time.
You sure? 'Cause
Yeah.
You're like right in the middle of something.
I know,
Ah,
but
okay.
I can't upload it if it's much longer, so she'll
Okay.
pull the next one right up.
Okay.